Assalamualaikum Dr. Tuan Nur Hafizah. Welcome to our online presentation. We are excited to introduce our team and share our project on data mining process, focusing on clustering and analyzing hypothyroid data. Our group members are Adam, Noraini, Fakhruddin, Tasnim, and I am Akila. In this presentation, we will discuss the data mining process and how clustering techniques can be used to analyze hypothyroid data. We'll start with the introduction and then delve into the details of our analysis.
The dataset for this project was obtained from Kaggle and provided by Baseline EBIT through the QMUL Data Science Society. Its purpose is to address the global lack of awareness regarding screening for hypothyroidism in adults. This dataset collects information on the prevalence of hypothyroidism in adults through questions and background inquiries. Diagnosis of hypothyroidism is determined based on laboratory tests, where blood test is essential to diagnose whether individuals have hypothyroidism or not. Adults with hypothyroidism are recognized to be at a heightened risk of experiencing various health complications, including severe depression. Although initial hypothyroidism research primarily focused on the children, it's, it's now acknowledged that hypothyroidism is a lifelong condition with significant implications for adult health. Increased awareness efforts have led many individuals to recognize potential symptoms of hypothyroidism in themselves, offering relief by providing answer to long-standing health concerns. Additionally, many individuals may have been misdiagnosed with other conditions or have never received an official diagnosis that aligns with their symptoms. I would like to explain a little bit about what is thyroid is. The thyroid is a small butterfly-shaped gland in the neck, just in front of the windpipe trachea. It produces hormones that affect things such as heart rate and body temperature. Meanwhile, thyroid gland creates abnormal type of thyroid hormones like as hypothyroid and hyperthyroid. I would like to explain a little. Our research is focused on hypothyroid. Hypothyroid is a condition when the thyroid gland does not produce enough of certain crucial hormones. This makes metabolism slow down. Also called underactive thyroid. Hypothyroidism may not cause noticeable symptoms in the early stages. Over time, untreated hypothyroidism can cause a number of health problems such as obesity, infertility, shortness of breath, and heart disease. Okay, let us focus on problem statement of this research. Hypothyroidism, a condition where the thyroid gland is underactive, is common in adults, especially women. Diagnosing it is difficult because there are no precise biomarkers, and doctors have to rely on symptoms, medical history, and thyroid function tests. This makes it hard to identify and treat the condition early. Using data mining technique to develop better diagnostic tools could help doctors predict and diagnose hypothyroidism more accurately, allowing patients to receive timely care and support. Validating these techniques with existing data can improve their effectiveness and ultimately enhance the quality of life for those with hypothyroidism. We have two objectives of the research, which are to identify similarities among hypothyroid patients using clustering method. Second, to provide the sample implementations of various clustering techniques used in thyroid data to improve the design of clustering methods for further enhancement.
Next, we go to the data preparation. In this dataset, have total attributes is 28, that involving 23 nominal attributes and 5 numeric attributes. For the nominal attribute, we have age, sex, on thyroxine, query on thyroxine, on anti-thyroid medication, sick, pregnant, thyroid surgery, L131 treatment, query hypothyroid, query hyperthyroid, lithium, goiter, tumor, hypopituitary, sick, thyroid stimulating hormone measured, triiodothyronine measured, total thyroxine measured, thyroxine utilization rate measured, free thyroxine index measured, referral source, and binary class thyroid stimulator. While the numeric attribute, we have thyroid stimulating hormone, triiodothyronine, total thyroxine utilization rate, and free thyroxine index. Next, we go to identifying missing value. Although this data is well documented and maintained, it contains some missing or noisy value. The dataset showed that the attribute set had 150 missing value, which account for 4% the data. The dataset contains several missing value shown as blank spot or gap in the table. We go to how to deal with missing value. First, we select choose filter, then we select unsupervised attribute, and we find replace missing value, and lastly we apply. After we remove missing value, the dataset show that the attribute set has 0 missing value. Second pictures show a fully populated dataset with no gap, whereas the previously missing value have been replaced using replace missing value filter. To enhance the analysis and interpretation of data, discretization was performed on the each attribute. This process involved converting and continuous each data into discrete categories. In each attribute, there are 92 distinct values. How to deal with this is, first we select choose filter, then we select unsupervised attribute, and we find discretize. Then we change attribute indices to 1 because H at attribute number 1, and B to 3 because we want to make it in 3 categories. Lastly, we apply. This image show after discretize and before labeling. To naming the label, we must save the dataset as CSV file and open it in Excel. Then we click Add, Find and Select. Next, we find and replace it. I choose one class label, so I choose negative infinity to 0.333. Then I copy a label and paste at find one. After that, I click replace with, and I replace the label with young. So all the label with negative infinity to 0.333 is replaced with young. Next, I choose 0.333 to 0.667. Then I copy a label and paste at find one. After that, I click replace and I replace the label with middle. Lastly, I choose 0.667 to infinity. Then I copy a label and paste at find one. After that, I click replace with and I replace the label with all. This image show after discretize and after labeling. Next, we go to identifying outlier and extreme value. First, we select choose filter, then we select unsupervised attribute, and we find interquartile range. And lastly, we apply. This image show the outlier and extreme value. Next, how to deal with the all of outlier that have in this data is, first we select choose filter, then we select unsupervised instance, and we find remove which value. In properties, we change attribute index to 30 and we apply it. Lastly, we delete outlier attribute and extreme value attribute by select it and remove it. Next, we do normalization. Normalization is an important data transformation technique in data mining that adjusts numerical features to a standard range, typically between 0 and 1. To deal it, first, we select choose filter, then we select unsupervised, attribute and we find normalize. In properties, we change scale to 1 and translation to 0. Lastly, we apply it. Next, we do data selection. Firstly, we select attribute and select choose add attribute evaluator. Then we find info gain attribute evaluator and we start. Next, from the result that we get, we choose top 7 attributes including binary class. Then, the attribute that is not selected is removed by select it and remove it.
In WEKA, clustering method like k-means, single linkage hierarchical and complete linkage hierarchical clustering utilize different distance measures such as Manhattan and Euclidean distance to determine how data points are grouped. K-means clustering use this distance to partition data into k-cluster with Euclidean distance measuring straight line distance and Manhattan distance measuring along axis suitable for grid-like data. Single linkage hierarchical clustering forms cluster based on the closest point between different clusters, with Euclidean distance useful for compact clusters and Manhattan distance capturing elongated shapes. Complete linkage hierarchical clustering groups clusters based on the farthest point, with Euclidean distance creating well-separated clusters and Manhattan distance maintaining overall clusters compactness. These methods, combined with distance measures, provide flexibility for various data types and clustering needs.
First, we have to open file and select the CSV data file, and we have to click the data clean.csv. Total attributes 28. Then we go to cluster and we have to choose filter k-means. So we have to change the display std diff to true, choose Euclidean distance, number cluster 2, and then OK. Our classes to cluster evaluation and then start. So we have to include cluster instances 41.061%, and then we repeat it for Manhattan and so on. Then we go to hierarchical cluster, link type single, distance function Euclidean distance, number cluster 2, and then OK. We have to start hierarchical cluster, single and complete. Need more time to digest the data because it's long. So we have to repeat this for Manhattan, Euclidean Manhattan for simple k-means, and also hierarchical single and complete. Repeat it for number of cluster 4 and 6.
This study applied the simple k-means clustering algorithm with Euclidean and Manhattan distances in the WEKA software. Using k values of 2, 4, and 6. For k equal to 2, using Euclidean distance, the data set of 3,770 instances was divided into two clusters, cluster 0 and cluster 1, with 41.061% instances incorrectly clustered. Key attributes like referral source and FT1 influence cluster centroid, with mean FT1 values of 0.276 for cluster 0 and 0.2724 for cluster 1, and the model built in 0.2 seconds. For k equal to 4, clusters were divided as cluster 0, cluster 1, cluster 2, and cluster 3 with a high error rate of 52.65% and a model build time of 0.46 seconds. With k equal to 6, the distribution of instances across clusters varied, with cluster 3 having the highest numbers of positive instances and the model built in 0.09 seconds. Using Manhattan distance for k equal to 2, cluster was similarly divided with 40.6101% instances incorrectly clustered and a build time of 0.14 seconds. For k equal to 4, the error rate was 53%, highlighting a significant mismatch with true class labels with the model built in 0.14 seconds. Overall, while the model built quickly, high error rates suggest a need for further refinement or different clustering approaches to improve accuracy. This study applied single-linkage hierarchical clustering using both Euclidean and Manhattan distances in WEKA with k values of 2, 4, and 6. For k equal to 2, using Euclidean distance, cluster 0 contained 100% of the data, which is 3,769 instances, and cluster 1 only 1 instances, with a model build time of 127.91 seconds. For k equal to 4, cluster 0 again held nearly all instances, with cluster 1, 2, and 3 each containing 1 instances, leading to an error rate of 7.7454% and a build time of 120 seconds. For k equal to 6, the distributions was similar with cluster 0 containing 3,765 instances and cluster 1 through 5 each containing 1 instances, resulting in a 7.7984% error rate and a build time of 122 seconds. Using Manhattan distance with k equal to 2, cluster 0 included 100% of the data, similar to the Euclidean result, with a 7.6923% misclassification rate and a build time of 2077.51 seconds. For k equal to 4, the distribution was again predominantly in cluster 0, which is 3,767 instances, with a 7.7454% error rate and a build time of 126.65 seconds. Finally, for k equal to 6, cluster 0 contained 3,765 instances with an error rate of 7.8% and a build time of 129.8 seconds. In all cases, cluster 0 predominantly contained instances from class B, while other clusters had negligible representations, indicating potential issues with the clustering approach. This study applied complete linkage hierarchical clustering using Euclidean and Manhattan distance in WEKA with k values of 2, 4, and 6. For k equal to 2, using Euclidean distance, cluster 0 contained 100% of the no class and cluster 1 contained 100% of the yes class, but 10.6% of instances were misclassified, and the model built in 98.73 seconds. For k equal to 4, the distribution was 86% in cluster 0, 10% in cluster 1, 4% in cluster 2, and 1% in cluster 3, with a 20.56% error rate and a build time of 66.3 seconds. For k equal to 6, 65% of instances were in cluster 0, 16% in cluster 2, and 10% in cluster 1, with a 40.19% error rate and a build time of 48.13 seconds. Using Manhattan distance for k equal to 2, cluster 0 contained 90% of instances and cluster 1 contained 10%, with 16.68% error rate and a build time of 71.56 seconds. For k equal to 4, the distribution was 76% in cluster 0, 13% in cluster 2, and 10% in cluster 1, with a 28.94% error rate and a build time of 46.04 seconds. Finally, for k equal to 6, 72% of instances were in cluster 0 and 15% in cluster 3, with a 33.57% error rate and a build time of 56.62 seconds. High misclassification rate in all scenarios suggests the need for parameter optimization for better clustering performance. Therefore, while no method achieves perfect clustering, the simple k-means algorithm with Euclidean distance and k equal to 2 offered a practical compromise with its efficient build time and moderate accuracy, making it the best choice for this data set and context. Further optimizations and tuning might still be necessary to improve the clustering accuracy.
For reduced dataset, we repeat the same step, open file, and then select the file clean new. We have 7 attributes. Then we click cluster, and then we select the filter, simple k-means, and then we change the false to true and choose Euclidean distance, number cluster 2, and then click OK, and choose classes to cluster evaluation, and then start. So we have the incorrectly clustered instances, and then we repeat same, but we change the Euclidean to Manhattan, number cluster same too, and then OK, click start. So we have the incorrectly clustered instances, and then we change the filter. We go to hierarchical clusterer. We choose Euclidean distance, single, and then number cluster 2, and then start.
Based on the analysis of k-means clustering using both Euclidean and Manhattan distances on the reduced dataset, several key observations can be made. For k-means clustering with Euclidean distance, starting with K2, the dataset for 3,770 instances was divided into two main clusters. Cluster 0 with 463 instances, 12%, and cluster 1 with 3,307 instances, 88%. The clustering resulted in an error rate of 19.52%, with 736 instances were incorrectly classified. Attributes like on tyrosine and query hypothyroid show distinct differences between clusters, with cluster 0 predominantly marked as false and cluster 1 as true. Class distribution reveal cluster 1 mainly associated with the positive class P and cluster 0 with the negative class N, highlighting clear distinctions but with no notable misclassification. Increasing K to 4 expanded to clustering into 4 clusters, cluster 0, 12%, cluster 1, 53%, cluster 2, 5%, and cluster 3, 30%. However, the error rate significantly increased to 43.61%, indicating substantial misclassification across clusters. Attributes and class distributions varied, showing mixed accuracy in separating instances into meaningful groups. Further increasing K to 6 produced 6 clusters with varied distribution. Cluster 0, 5%, cluster 1, 40%, cluster 2, 42%, cluster 3, 2%, cluster 4, 4%, and cluster 5, 8%. The error rate soared to 55.9%, reflecting challenges in accurately grouping data points despite the increased cluster granularity. Attributes and class mapping further illustrated complex pattern with high misclassification rate. Switching to k-means clustering using Manhattan distance, similar patterns in clustering and attribute distinction were observed as with Euclidean distance. For K2, the dataset was divided into two clusters. Cluster 0, 82% of data, and Cluster 1, 80%. The separation between classes P and N was clear, but the clustering resulted in an error rate of 22.31%. With 841 instances incorrectly clustered, the computation time was 86.54 seconds. For K4, with Manhattan distance, the dataset was segmented into four clusters. Cluster 0, 81% of data. Cluster 1, 11%. Cluster 2, 6%. And Cluster 3, 2%. While Cluster 0 predominantly contained instances of Class P, Cluster 2 had more instances of Class N. However, 912 instances were incorrectly clustered, resulting in a 24.19% error rate. The model took 437.74 seconds to complete. Lastly, for K6, with Manhattan distance, 6 clusters were identified. Cluster 0, 81% of data. Cluster 1, 11%. Cluster 2, 4%. Cluster 3, 2%. Cluster 4, 2%. And Cluster 5, 0%. Despite effort to distinguish classes, 950 instances were incorrectly clustered, leading to a 24.27% error rate. The model's construction took 472.76 seconds. In conclusion, k-means clustering with Euclidean distance and K2 stands out as the preferable choice for clustering the reduced dataset. It achieved a relatively lower error rate of 90.52% compared to higher values of K, indicating better separation of clusters and more accurate classification of instances, while increasing K attempted to capture finer distinctions in the data. It led to significantly higher error rate without substantial improvement in clustering accuracy. Therefore, for this dataset, the simplicity and effectiveness of K2 with k-means clustering using Euclidean distance make it the optimal choice for clustering analysis. In our analysis using single hierarchical clustering with Euclidean distance, the result for K2 show that the model built in 392.87 seconds grouped the majority of instances, 98% into cluster 0 and the remainder 2% into cluster 1. Most instances in cluster 0 corresponded to the majority class P, while cluster 1 contained the minority class N, with an error rate of 9.7%. For K4, built in 737.9 seconds, cluster 0 held 83% of instances, mainly class P, while other clusters show a mix of classes, resulting in a 22.55% error rate. With K6 completed in 468.86 seconds, the largest cluster still contained 83% of the instances, and the error rate was 22.57%. Similarly, using Manhattan distance with K2, the clustering process took 684.26 seconds, and the model grouped most class P instances in cluster 0 with a 9.7% error rate. For K4, built in 437.74 seconds, the largest cluster also held 83% of instances, and the error rate was 22.55%. Finally, for K6, completed in 472.76 seconds, the largest cluster contained 83% of the data, with an error rate of 22.60%, Overall, the models show that increasing K generally led to higher error rate, indicating most complex clustering pattern. In the analysis using complete hierarchical clustering with Euclidean distance, the results for K2 show two clusters, cluster 0 with 3,755 instances, mostly class P, and cluster 1 with 50 instances, mainly class N, completed in 83.36 seconds with an error rate of 8.12%. For K4, the clusters were more diverse, with cluster 0 containing most class P instances, while class 1 had more class N instances, leading to a higher error rate of 19.95%. At K6, cluster 0 still dominated with 83% of the data, but the error rate increased to 22.92%, indicating more complex pattern. Using Manhattan distance, for K2, cluster 0 had 3,130 instances, predominantly class P, and cluster 1 had 640 instances, mainly class N, with an error rate of 22.31% over 86.54 seconds. For K4, cluster 0 again had most class P instances, while cluster 2 had most class N, resulting in an error rate of 24.19%. At K6, the pattern remains similar, with cluster 0 holding most class P instances and an error rate of 24.27%. Overall, increasing K led to a more complex clustering structure with higher error rate. In this analysis of K-means and hierarchical clustering on a reduced dataset, we evaluated both Euclidean and Manhattan distance metrics with different cluster counts, K equal to 2, 4, and 6. The simple K-means algorithm showed that as K increased, error rates also rose, indicating more complex data structures. With Euclidean distance, the error rate ranged from 19.52% at K2 to 55.9% at K6. Manhattan distance exhibited similar trends, with error rates increasing from 19.52% at K2 to 61% at K6. Hierarchical clustering results show that using Euclidean distance, the error rate increased from 8.12% at K2 to 22.92% at K6. With Manhattan distance, error rates rose from 22.31% at K2 to 24.27% at K6. Overall, K-means clustering with Euclidean distance at K2 had the best balance of error rate and simplicity, making it to be preferred method for this dataset.
Hello everyone, my name is Adam Farhad bin Saifur Azwan, and today I'm going to explain to you about the clustering visualization using Weka. Okay, these two images below are the representation of the result after applying K-mean clustering to the dataset. Both visualization, both picture, use instant number as the x-axis and the binary class as the y-axis. With the cluster is color coded to red and blue. In the first image, we can see that cluster are blue square and red crosses. This visualization show a scattered distribution of instance along the x-axis, with a dense accumulation at the bottom and more spread distribution toward the tops. This indicate that the presence of two main clusters which are intermixed throughout the datasets. The clustering seems to have not effectively spread the data into the group as indicated by the overlapping of blue and red marker. However, the second image also show cluster with blue and red color, but with additional preprocessing applied after the data reduction. This preprocessing likely involve the filtering and attribute selection, which aim to improve the clustering results. However, similar to the first image, there is still a significant overlap between these two clusters.
Although the top part of the plot appears slightly less clustered, this might suggest that the preprocessing had effect in the attempt to distinguish the differentiate the cluster. However, for the hierarchical clustering and for hierarchical compact clustering and hierarchical singlet clustering, we cannot visualize the dendrogram. This is due to the large number of instances to generate the dendrogram, which consume a lot of memory. That's all.
Assalamualaikum. My name is Nur Akilah binti Abdul Farouk, and in this slide I will explain about the model evaluation in generating confusion matrix. Model evaluation in data mining assess the performance and reliability of predictive models. It involves splitting data into training and test sets using cross-validation and applying various metrics such as accuracy, precision, recall, and F1 score. The confusion matrix provides a detailed breakdown of true positive, true negative, false positive, and false negative. Evaluating models help identify overfitting, which is models that are too complex, and underfitting, models that are too simple, ensuring the model generalize well to new data. Effective evaluation aids in selecting the best model, improving its performance, and ensuring its reliability for real-world applications. Using Euclidean distance with two clusters simplifies the problem, making it easier to interpret and understand the clustering result. It provides a clear binary classification, which is straightforward to evaluate using a confusion matrix. In this confusion matrix, we are used three method, which is k-means Euclidean distance k equal to 2, single hierarchical Euclidean distance k equal to 2, and complete hierarchical Euclidean distance k equal to 2. In k-means Euclidean distance k equal to 2, this matrix shows that out of the total instances, 3025 were correctly identified as positive and clustered into cluster 1, while 454 positive instances were incorrectly placed in cluster 0. Similarly, 9 negative instances were correctly clustered into cluster 0, but 282 negative instances were incorrectly placed in cluster 1. These metrics highlight that the model performs well in identifying positive instances, but has some room for improvement in minimizing false positive and false negative. For this model, the accuracy would be 80.4778%. Next, in single hierarchical Euclidean distance k equal to 2, the results indicate that 3,425 instances correctly identified as positive and clustered into cluster 0, while 3 instances correctly identified as negative and clustered into cluster 1. Moreover, 288 instances incorrectly identified as positive but belong to the negative class and clustered into cluster 0, while 54 instances incorrectly identified as negative but belong to the positive class and clustered into cluster 1. The model has an accuracy of 90.93%, meaning most predictions are correct. The confusion matrix highlights where the model performs well and where it needs improvement. Lastly is the complete hierarchical Euclidean distance, k equal to 2. The results show that 3,464 instances correctly identified as positive and clustered into cluster 0, while 0 instances correctly identified as negative and clustered into cluster 1. The model also indicates that 291 instances incorrectly identified as positive but should be negative and clustered into cluster 0, while 15 instances incorrectly identified as negative but should be positive and clustered into cluster 1. For this model, the accuracy would be 92.16%, reflecting a mostly effective classification of positive instances but with some misclassifications. That's it from me for model evaluation.
Hello everyone, and now I'm going to explain about clustering analysis. From the comparison of the different models using both full and reduced dataset, several key insights emerge. Firstly, in terms of accuracy, the simple k-means model show a dramatic improvement when the dataset is reduced, indicating its benefits significantly from a more concise dataset. Hierarchical single maintain a high accuracy for both full and reduced datasets, with a slightly improvement for the reduced dataset, as you can see in the picture below. Hierarchical single exhibit high accuracy with the reduced dataset, but experience a slight drop with the full dataset. Graph comparing the time taken to generate model of a different model using different dataset. In terms of time efficiency, simple k-mean is the fastest model to generate, making it ideal for scenarios where time is critical factor. Hierarchical complete take a long time with the full data set, but show a significant improvement with the reduced data set. Hierarchical single take the longest time after data reduction. Given our preference for efficiency and importance of handling a large amount of data, simple k-mean with the reduced dataset is the best choice for us. This model has the fastest time to generate, which is approximately 0.11 seconds, making it well suited for processing our large dataset. Although its accuracy is slightly lower than hierarchical complete, it achieves a relatively high and acceptable accuracy of around 80.5% after data reduction. This indicates that necessary for a thorough this indicate that reduction method retain the most relevant attribute necessary for a thorough analysis. Using simple k-mean model with the reduced data set in Weka ensure that we can handle large volume of data quickly while maintaining a satisfactory level of accuracy. Okay, hello. And next is for our interpretation of our work. Our cluster analysis of hypothyroid patient revealed two separate groups, with each with unique features and treatment stages. Cluster 0 contained 463 individuals, making up 12% of the sample. None of the people in this cluster are using thyroxine, although a significant number, which is 87%, have tested for hypothyroid, indicating a diagnosis suspect. They are aware of the illness. We see higher mean level of TSH and TT4 and FTI in this cluster, indicating a more severe case of hypothyroidism that has not yet been treated, but they are aware. And next, for the cluster 1, which is 3,307 individuals, accounting for almost 88% of the sample. All individuals in this cluster are aware and taking thyroxine, and the vast majority, which is 94 of them, have tested for hypothyroidism, indicating that the illness is being managed and being treated on an ongoing basis. This means TSH and TT4 and FTI levels are slightly lower in this cluster, indicating that these patients are likely managing their illness with therapy. Next, this research suggests that cluster 0 is most likely made up of individuals who have been diagnosed with hypothyroidism but have not yet begun the treatment, as demonstrated by the elevated thyroid function indication. Cluster 1, however, contain patients who are already taking thyroxine and have better control of their thyroid function level. That's all.
In conclusion, the k-means clustering analysis of the hypothyroid dataset with K2 clusters and Euclidean distance effectively transform raw data into actionable insights. Extensive preprocessing, including data selection, cleaning, normalization, and handling missing values, prepares the data for analysis. The clustering reveals significant insights, with one cluster predominantly containing hypothyroid positive patients and the other hypothyroid negative patients, converting information into knowledge. These insights help healthcare professionals improve diagnostic and treatment strategies for hypothyroid condition by tailoring patient care more effectively. The method's effectiveness highlights the importance of thorough data preparation and analysis in extracting meaningful patterns and guiding informed medical decisions. Thank you.